Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, in the previous two lectures, we have studied about the basic SR latch, where we saw the NOR implementation and the NAND implementation. And today, we move on further because we said that in our computer science, all the devices are actually synchronous. That means they have the clock with it. So there's no such device in computers which doesn't have a clock. So SR latch serves as a basic building block for the flip-flop, but the actual thing is the flip-flop, where we have the same SR latch but with the clock. But if we talk about the basics of the circuit we saw last time, okay, and we said this is my, say for example, NAND gate, and this is the another NAND gate, okay. Now look at it. This is having the one input here and other input here. Then its output is actually going the input here, the feedback loop, and its output is going as the input to this gate, right? So this has some kind of feedback mechanism here. And we saw that we said this is our R, and we usually call it S, for example. And then we said that in the if we see the NAND's truth table, and we say this is A and this is going to be B, 0, 0, 0, 1, 1, 0, 1, 1, and we know the AND, okay, of this, if we say AND of the zeros, where there is zeros is going to be the 0, but if the NAND of it, it will be the 1, and only this one, when it is a 1, 1, okay, the NAND of it will be 0, because AND of it will be 1, NAND will be 0. So the dialog we said was, if one of the inputs is 0, output is going to be 1, okay. And using this truth table, and we saw that if my top side, that is R, if R is 1 and S is 0, this is going to set, this is Q complement. So what does the set mean? Set means when the Q is 1 and Q complement is 0. So we know this excitation table of it. We usually call it excitation table, that if R and this is my S, this is going to be Q and Q complement, and then state. I know if R is 1 and S is 0, it is going to reset because R is 1. So that means this is 0 and 1. So this is called a reset state. Now if R is 0 and S is 1, in that scenario, it's going to set. So set means Q will be 1 and Q complement will be 0. We had discussed this in the last topic, okay. And in case of my NAND, if I have the 1, 1 state, that was the memory state. So if I have in between the 1, 1, that's going to be, if I have the 1, 1 in this scenario, if after this, so it will have whatever the previous state is, so it will repeat the previous state, so it's called a memory state, okay. We know the excitation table, we had discussed it the last time, and here the 0, 0 was not allowed, because we know one of the inputs is 0, output is going to be 1. So if it is 0 here and 0 here, so output is going to be both 1, 1. So that will be the race condition. So it's not allowed, it's a race condition. Now I want to improve on this thing. I want to improve this thing. So I would like firstly to add up a clock here, because it's not having a clock. So that's not a good idea to build the circuits without clock. The second thing is, I do not want this 0, 0 state here in this scenario, in the NAND gate. In case of NOR gate, it was the 1, 1 state which was the race condition. If you have not watched the previous two lectures, you should watch first that, then come back here. Otherwise, you will understand nothing. Now, the question is how I do this. I want to also change the behavior of this NAND gate in the sense that I am saying 1, 1 is my memory state, okay. I can keep it 1, 1 as memory state, but I would like that 0, 0 should be memory state, like we had in a NOR gate, the 0, 0 as a memory state and 1 1 is a not allowed state. And later I see that I do not want this 1 1 state at all. Okay, so if I do not want this 1 1 state at all, that thing is called the D flip-flop. Just giving you a little idea. And later we see that even this state, which is not allowed, because it is showing some kind of a behavior, being a computer science students, we use everything to our advantage. So this 1 1 state, which is in fact here the 0 0 state, okay, in case of NAND, which is not allowed, is a race condition. I will use this to build our circuits like counters and all. We will see that later. So we will use this also. But firstly, because this is not allowed in unreliable state, I would like to remove it. So that will be in a D flop. That's called a D flip-flop. So that is a step next. In a step first, what we are doing is we are trying to add up a clock to this circuit. We want to add up clock to this circuit. But we have to remember one thing. So if you forget R and S, it is R here and S here, right? You forget about it. We know one thing, that if the top side is 1 and bottom side is 0, because we know the top side 1 means reset. So it is going to be the reset state, that is this state. That means if top side is 1, bottom side is 0, here the input to this gate, to this latch, if the top side is 1 and bottom side is 0, okay, it's gonna be the reset. Instead, if the bottom side is 1, that means set side it is 1 and reset side it is 0, it's gonna do what? It's gonna set. So remember that thing. I repeat. Because we don't want to, what we have generated in our previous video, we don't want to do that, repeat that all the time. Now we remember this thing. We remember this thing. That if the top side is 1, it is 0. So it's going to reset. That means it will have the Q0 and Q complement 1. And if instead it is here 0 and here it is 1, okay, then it's going to, if top side is 0, that means R side is 0 and S side is 1, it is gonna set, because we know this is S and this is R. Now immaterial R and S, I don't worry about R and S. This is the names we have given. We don't worry about this is R and this is S. Basically the thing is output, Q and Q complement. So we remember this flip-flop, latch, if the top side is 1, bottom side is 0, it's gonna reset because R side is 1. And the second thing is, if the top side is 0 and bottom is 1, this input is 1, that is S is 1 and R is 0, it is gonna set. Set means Q will be 1 and Q complement 0. So this is my set state. Does make sense? Now we want to add up a clock to it. Okay? If we add up a clock to it, but the behavior should be same. Okay? Behavior should be same. So how can I do it? So what I do here is, let me build this again, this circuit. Okay, let me build this circuit again. Little down and little right. Let me clean this here properly. Yes. Now let us build this circuit again properly. So say this is my NAND gate 1 and NAND gate 2, and I have input here and input here. Okay. Now they have a feedback loop. I know this is a feedback loop, so I may use a crisscross feedback loop right now. Okay, I got a feedback loop. Now this is my basic latch. Okay, this is my basic latch. Okay, but I'm not giving it input here. Rather, this was my basic latch, which is showing the behavior. If I rub it for a while, I don't need to show it like this. Okay, this is my basic latch having the feedback loops here and here. Okay, and now I want to add up a clock to it, and I know this behavior. The behavior of it is, if the top side is 1, it's gonna reset. If the bottom side is 1, it is gonna set. If S it is 1 and 0 here, it is gonna set. If 1 is on a top, 0 is on a bottom is gonna reset. We know that. And for 0 0, it is gonna be not allowed, and 1 1 it is gonna be memory. The first thing is I want to add up a clock, and what the clock does is, if the clock is active, the circuit is enabled. If the clock is not active, the circuit is disabled. So how I do that? What I do for that is I will do one of the implementations. I use the AND gate here. I use another AND gate here, and I am getting these inputs via this AND gate, and with this AND gate I am tying together it with a clock. Okay, I'm putting a clock here. Now the inputs which are coming is from here to here. Okay, so this is same. Now only difference is I added up a clock. This was my, now I draw this. This was my basic that latch. It's the same latch. Okay, to this latch I'm adding the clock circuitry. The clock circuitry is using the two AND gates. Now why I do AND gates? Because if the clock is 0, the output should not be there. Say for example it was a 1 and 0 and the clock is 0. There is no clock. So AND gate को जब एक one of the inputs is 0 to the AND gate, output is gonna be 0. So it is immaterial, it is 1 or whatever. The output is gonna be 0, and here also when the clock is 0, whatever it is, 0 or 1, it doesn't matter, output is gonna be 0. So that means this flip-flop will be disabled. It is not taking inputs anymore. Does it make sense? So if this clock is 1, okay, if this clock is 1, that means clock is coming up, this voltage is there. Now whatever comes here, that goes out. So this, when the clock is there, this AND gate becomes transparent. Whatever the input comes, that goes out. See, if the clock is 1 and input is here 1 and 1 for the AND gate is 1. Say farz kijiye this was 0, okay, and clock is 1 now, 0 and 1, that is 0 for the AND. So whatever is here, that comes here. So it becomes transparent now. It is as if it is not there. If the clock is 1, as if there is no AND gates there, because whatever is coming, that is going through. Okay, so this will give us same result. Only thing we have added to this circuitry is this clock, and by clock we can control this circuitry. We can make it enabled or disabled, and we can make it work when we want to work. So if for example we don't want to use this, so we will keep the clock 0. It's not gonna work. Even the inputs are coming, if the voltage are input levels, but they're still, the circuit is disabled. This latch is disabled. Now we will not call it latch, because to this latch, because this was a latch, right? This was a latch, and this is a clock. When you got a clock plus latch, this is our flip-flop. Remember that thing, we have a flip-flop. Because we got a latch, basic latch, and we got the clock, right? Does it make sense what I'm saying? And rest, it will have the same characteristic table, because 0 is coming up. So we know if, for example, here comes the 1 0. I need to clean this for a while. Okay, let me clean this properly. Okay. Now this is a full circuit. I was showing that this is the latch plus clock, but now this is a full, and this will be called as a flip-flop. Okay, so I don't need to put up this thing here, because this is not my any more latch. It was just showing that this is latch plus clock. This is the full circuit, and this thing is called as a flip-flop now, because it has the basic latch structure and the clock. Okay, and clock used using the AND gate. Okay, because AND gate, if the clock is 1, the AND gate becomes transparent. Whatever comes here goes here. Whatever comes here goes here. Does it make sense? It's very simple now. Now rest is same. Rest is same. The characteristic, we don't call this thing as a truth table, we call the characteristic table. What will be this was my characteristic table of the latch. Now we have also the clock with it. So we have to add up to this structure the clock. We have to say clock, C-L-K. We got a clock. Okay, let me draw the characteristic table on this side. Okay, so this is my, I can go this much of screen I have. Okay, I will put it on top. I got a clock, and then I got the, maybe I call it R and I call it S. It has no effect because it's the same what we had in a latch. this is R and this is S, okay, and this is my Q and this is my Q complement, okay, and I will say the state. What is the state of the device? So if the clock is 0, if the clock is 0, it is immaterial what is coming up in the R and S, it is disabled. So that means whatever the R and S are, we are not taking any inputs, so it is disabled state, right? I'm not using anything here. My circuit is disabled, my flip-flop is disabled. And this thing again will be called as a characteristic table, not the truth table, right? Because characteristic table shows the behavior, how our circuit works on different inputs. Now if the clock is, say for example, if it is 0, okay, or say now it is 1, not 0, because if it is 0, it's not going to work. If it is 1, and my R and S are 0, 0, okay, and R and S are 0, 0, that is the same not allowed state. We will not be allowed to have this state. So we say this is going to be the not allowed state, and we know what is the race condition here. Why is it not allowed? This is the previous video, we already know that, so we don't need to repeat that, okay. You can go back anytime to the last video and see why the 0, 0 state is not allowed in the NAND implementation of the latch, and now it's a NAND implementation of the flip-flop. Why is it flip-flop? Because with the latch we got a clock circuitry. Otherwise the same old latch. Okay, nice. So now if the clock is 1, because if the clock is 0, nothing is going to happen. So only thing happens when the clock is 1. So if the clock is 1 and my R is 0 and S is 1, for example, R is 0, S is 1. So I'm putting R 0 and S 1 here. What will happen? And if the clock is 1, if the clock is 0, then it doesn't, whatever the inputs are, they will not go to the output because this AND gate will block them. But if the clock is 1, then whatever the input is, that will come here. So this AND gate will become transparent for the inputs. क्योंकि AND में अगर ये 1 है, तो अब अगर ये 0 है तो ये 0 हो जाएगा. अब अगर ये 1 है तो ये 1 हो जाएगा. So whatever R is, that will come up here. So that means this 0 and this 1 will come up here. If it is 0, 1, the 0, 1 will come up here. Now when the 0, 1 comes up here, we know in our circuitry, in the latch, the bottom side is 1. Okay, it's gonna set because bottom side is 1. If the top side is 1, that's R side is 1, it's gonna reset. We have worked it out in the previous video. You can go there and watch it. Now this is 0 and 1, so that means it's gonna set. So if I got a 0 and 1, it makes sense, S is here. So it's gonna set. Set means Q is 1 and Q complement is 0, and we call it a set state, and we are done. Now if I don't have the 0, 1 state, I have a 1, 0 state in a state. So what's gonna happen? So if I have a clock 1 and I have a 1, 0 state, and 1, 0 means what? R is 1, so we know R is a reset. So it's a 1 and this is 0. We know if the clock is 1, now AND gates will be transparent totally. The whatever is here, it comes here. So 1 and 0 is here, it comes here, 0. So when for this latch, okay, when the top side is 1, what's going to happen? It's going to reset. We know that. It's going to reset. That is 0, 1. That is Q will be 0, Q complement will be 1. So it's going to be reset state. Okay. We can add up the memory state. We have not added up. We should add up first the memory state before we go to the set. From set to reset, we should add up the memory state. And for us, what is the memory state? Memory state is 1, 1. 1, 1 is the memory state. What is the memory? If both are 1, 1 here, okay, and it will come up here as a 1, 1. Because if clock is 1, so all the time the clock is 1, then only, okay. If it is 1, 1, it will come at 1, 1. The 1, 1 state memory state. What the memory state means? Whatever the previous state was, it will retain that. So it will stay as 1, 0, and it will stay as set state, and we actually call it as, it's not a set state, it will stay as set, but this state itself will be called as a memory state. Because this state itself will be called as the memory state. Okay. Now same is with the clock is 1. Now we got a 1, 0, that means R is 1, and this is 0, so 1 0 will come up here. So this is gonna be the reset, because top side is the 1. It's gonna reset means q0 and q complement 1. This is gonna be reset, and if have a clock 1 and then you have a 1 1 here, okay, it's a memory state, so it retains the previous state, so it will retain this state here as 0 1, and this will be called again as a memory state. Okay, does make sense? Now I am wonderfully applying the same SR logic in my flip-flop, SR flip-flop. We will call it as an SR flip-flop. So this is my SR flip-flop. Okay? But now I want a little change here. The first change I want is I want S on a top and R on a bottom. Okay? Because the way my latch works, I have to keep R on a top and S on a bottom. For the latch, we cannot help it out, it has to be like that. But from here, this side, because what I work, okay, I work on, like for example, we have on this side the decimal and computer converts into binary. But on my side is a decimal because I work in decimal. Same is there, I'm looking Q is here and Q complement is here, and for me when it is set, when it is set, I am putting Q as 1. When it is reset, I am putting Q complement as 1. So that means set means when the Q is 1. And Q is here, but the S is here. So it doesn't look good, because I know the functioning of circuitry, I have to keep S down. Okay, I have to keep S, it only becomes set when this downside is 1. So that means I have to keep S1 this side. So I know this flip-flop, this latch, inside latch means without the clock. This is gonna work like that. How it gonna work? If bottom side is 1, okay, it is gonna if bottom side is 1, it is gonna set. That means Q becomes 1. And if bottom side is 0 and top side is 1, then Q complement will become 1. Okay, we can't help it out, the circuitry works like that, but we can work on here, because which is for the user. I want not R here and S here, I want S here and R here. So I want to flip it. But how I will flip? I have to do something, no? S and R. But say if S is 1, okay, 1 goes on this side and becomes 1, and R is, say for example 0, it goes here, and I think, hey, S is 1, so it should set. But ye flip-flop, this part of the circuitry, I know the latch, if the top side is 1, it's gonna reset, it's not gonna set. That's a problem. So I should do something. Number 1 was that thing. Number 2 is the 1 1 state. The memory state is my 1 1 state. Okay, I have a 1 1 state. Okay, I don't want the memory state to be 1 1 state, because 1 1 again means some kind of a voltage. I have to provide voltage to store things in it. But rather a memory should be such that if we remove the voltage to store things from me. So it should be like a NOR. In a NOR we have 0 0 as memory state and 1 1 as the excitation or race condition. So I do not want the memory state to be 1 1, rather 0 0. Because when I remove the voltage, it becomes 0 0, and it should be my memory state. So I want to work on that. So how I will work to fix it here, so that the same circuitry will be used for us. I had to do nothing. I thought I keep this space open. I thought I will make another diagram, but I don't need to make another diagram, because the only thing I do is here, I will use a NAND gate, not AND gate. I will use the couple of NAND gates here now. Okay, let me rub the things and see how it will work. And when I use the NAND gates, not the NOR gates, okay, maybe I use a different circuit and show it there. Okay, why keep it like this? Because it will keep ticking in the brain. This was my R and this is my S, because this keeps ticking in the brain, and we add up our different circuits. So what I do is I use firstly my couple of NAND gates, okay, and this is the input and this is its input. Where from the second input comes in, we know the second input is going to come from this output, will go into its input, okay, and this output is gonna come to its input like this. Okay, we know that. And then we have to add up a clock. So what I do with the clock is, now I'm not using AND, I'm using the NAND. I'm using all NAND gates, NAND and NAND. This is giving this input, it's here. And we have a clock. Okay, maybe I put up a different pin for the clock. So I got here, this line is tied with the clock. Now I do not call this as my R, I call this input as S and this input as R. Okay, it's not visible, so let me put up different pen. This is R and this is S. Now how is it going to work? How is it going to work? Because we know this part of the circuit, we know this part of circuit. If you talk about this part of circuit, okay, if you talk about this part of circuit, we know about this part of circuit. Okay, we know about this part of circuit, that this is a latch. In a latch, if top side is 1, okay, it's gonna reset, and if the bottom side is 1, it's gonna set. Okay, let us see. We will use it. We'll say, okay, you do your job. I'm not gonna mess up with you. You are 1 on the top, you're gonna reset. 1 on the bottom, you're gonna set. So what does set mean? Q is 1 and Q complement is 0. What does reset mean? Reset means that Q is 0 and Q complement is 1. And when will it set or reset? If the top side is 1, it's going to reset. If the bottom side is 1, it's going to set. We know that. So I'm not going to touching it. I'm going to see here. For me, if S is 1 and R is 0, the guy should set. Okay? This guy should set up if the S is 1. In this case, if the top side was 1, it was okay, and because the 1 will come here, and we know this part of a circuit, if 1 is on the top, it's going to reset. And we are putting the R here. We were saying, hey, it's a reset. But I'm not putting R here. Now I'm putting up S here. And I'm putting 1 there, and I want that it should set, not reset when I put a 1 on the top. Because this circuit works what is here and here, not on the here. Okay, because this NAND gate will do something to it so that it becomes what this requires. Because I want S to be set for this guy, for this circuit, part of circuit, the 1 should be here, then only it will set. It should be 0, 1, then it will be set. But I'm putting 1 here and 0 here, and I believe S should set me. But for this circuit, when 1 comes here, only then it will set. If 0 is here, it will only set. So 0, 1 should be there. Let us see if 0, 1 is coming or not. Because externally I'm putting S here. Now I'm putting S with inline of Q. It is making more sense, because S and Q, this is set and Q is for the set. This is R and Q complement is for the reset. They are in line now. It's making more sense to me, right? But it should work. Let us see, will it work or not? I'm putting a 1 here, and clock is 1. If the clock is 0, nothing is going to happen. If the clock is 1, okay, if the clock is also 1, so 1 and 1, what will AND gate? AND gate will make it 1 and 1. AND gate means 1. But what does the NAND gate do? It will flip it. It will make it 0. Okay. Now what about this? This was 0, 0, and this side clock is coming 1. 1 and 0 is 0 for the AND. But what will NAND do it? NAND will make it 1. So it is becoming 0, 1. And we know this circuit, if the 1 is on the bottom, it's going to set. Now here on this side, I'm putting S1 here, but after the NAND, it is coming 1 here, 0 here. It was 1, 0, it becomes 0, 1. It flips it. So for us, that's what we want. We want S1, but for this circuit, 1 comes here, it will set. Does make sense? It's perfect, right? So let's try to make its excitation table here. So what is this all about is actually, this is the NAND implementation, perfectly NAND, using the clock also with the NAND. And in this case, I put up S on the top and R on the bottom so that my S and Q are in line. It makes more sense. But inside is working the same old way. Inside is working the same old way. I'm saying, okay, you work on the same way. I will do something so that I flip these inputs. Okay, let's try to see it here. So this is my clock all the time. This is my R, this is my S, this is my Q, this is my Q complement, and this is gonna be the state. Okay, so if the clock is 0, so nothing, if the clock is 0, what's gonna happen? Nothing's gonna happen right here. So this is disabled. Okay, because if it is 0, let's try to figure it out. If it is 0, say this was 1. 1 and 0 is what? 1 and 0. Let us try to first see what will happen if it is 0. If it is 1, it is 0. So NAND gate will make it 1. Okay. Now whatever this was 0 and this is 0. 0 and 0. NAND gate will make it 1. So it's a 1-1 state. What's the 1-1 state to this latch? That is here. This is the latch. So 1-1 state is memory. So it will retain whatever the previous was. It will be like that. It's as if no input has come. If the clock is 1, both NAND, if the clock is 0, sorry, what I'm saying, if the clock is 0, both NAND gates will input 1-1. In that scenario, whatever was the previous output, because 1-1 is the memory state for this latch. I'm saying only this part of circuit, latch. That's a memory state, what we had done in the previous video. Okay, so it will retain the whatever the output was as if no input has come, because that they are not changing anything. So it literally it is disabled. So in fact, it is becoming a memory state here. If the clock is 0, it's becoming a memory state here. But for us, it's disabled because it's not, the inputs are having no effect. They are not changing the output, so they are having no effect whatsoever. So that means if I say clock is 0, it's gonna disabled. It is disabled. Okay, or we could write it as the memory state also. Now if the clock is 1, then something happens. If the clock is 1, now the clock, you keep the clock 1 all the time, 1. Now you put S and 0 or 0. First we did here 0 1, we did here 0 1, and we will also do here 0 1. Now I don't write R, I have written R first S. I can write it this way. I can write it first S then R, because I am putting first R now S. Or you can write S there, or it doesn't matter. हमें values देखने कहाँ पे क्या आएंगे. But now it makes proper sense because S first R बाद में. Now what I am doing is I am putting S as 1 and R as 0. And we know when S is 1, it will flip it, it will make it 0. It is 0, it will flip it, it will make it 1. 0 1. So we know bottom side is 1, it's going to set. That means Q will be 1 and Q complement will be 0. So it is a set state. Now again the clock is 1, and this is now if I have the we had memory state as 1 1, but we don't want that. We don't want to keep memory when to give some voltages of 1 1, because 1 means to give some voltage. We want 0 0 as memory, not 1 1. But inside this circuit, this will work only for, because this is the excitation table of this latch. The latch works for 0 0 as not allowed and 1 1 as memory. So if for latch 1 1 comes in here, it will act as a memory. But we want as an output on the outside, the 0 0 should act as a memory. But 0 0 for this latch is the not allowed state. Okay, but if we give 0 0, now this structure will give us here 1 1, and that will be memory state for this. So हम 0 0 पे काम कर रहे हैं, ये खुद 1 1 पे काम करके memory बन रहा है. Let us see it. So if it is 0 0, clock is but 1, clock, this is enabled, circuit is enabled. What is the NAND gate doing here? And will make it, when the input, one of the input is 0, and will make it false or 0, and NAND will make it 1. This also 0, and will make it false, and NAND will make it 1. So I'm getting 1 1 state. So what is 1 1 state for this? That's a memory, right? So in fact, as a user, I'm putting 0 0, but the NANDs are flipping it to make it 1 1, and for this circuit, 1 1 means memory. So that means if I put up here 0 0, okay, it is going to retain the previous output and it's going to be the memory state. Okay, and if the clock is 1 and I'm putting up here now the reset state 0 1, if it is 0 and this is 1, okay, that means I'm putting up here 0 and 1. Now what will the NAND do to the 0? Because 0 and means 1, 0, and NAND will make it 1, so this is 1. What about the 1? 1 0 again. 1 second. The clock is 1, okay? 1 and clock is 1. 1 and 1 is, for AND it is 1, but for NAND it is 0. So I am getting 0 1 here, but it is flipping it to 1 0. For this circuitry, 1 on the top, 0 on the bottom means reset. So that means Q will be 0 and Q complement will be 1. So this is going to be the reset state. And if I repeat my memory state here, again the 0 0, okay? If I put up here 0 0, the NAND will make it 1 1, and 1 1 we know for this circuitry is a memory state, so it will retain this state whatever the previous state was. So that is a memory state, okay? And what about the 1 1? Okay, if I make it 1 1, the NAND will flip it to 0 and 0, and 0 0 for this guy is not allowed. But for us now, it is not allowed when we are putting 1 1 here, because I am putting as a user 1 1. This clock circuitry makes it 0 0, and 0 0 is here for what? Not allowed. So that means if I am putting a 1 1 here, that is not allowed, a race condition. Right? So I have done a lot of things here. I have added to the basic latch the clock. We have added to the basic latch a clock circuitry to make it work whenever I want it to work. So whenever a CPU needs this thing, it can put up a signal. The control signal, the control mechanism we have, or a control unit, issues this voltage here for the clock, and this becomes enabled. And when it becomes enabled, these AND gates disappear. Okay, now to remove the few disadvantages here, what I did is I want not the 1 1 state as a memory state, rather 0 0 as a memory state. Okay, and I want on the top S and bottom R. I don't want R and S, because R is lined with this. That is wrong for us as a visual purposes. So I want S here and R here. So the S and Q are lined together, and R and Q complement are lined together, because S means set and R means reset. And for a set means Q is 1 and reset means Q complement is 1. So therefore R with the Q complement seems better combination, and S with the Q seems a nice combination, and we can achieve that if we use everything as a NAND gate. I'm using everywhere all the NAND gates. Okay? Okay. Now we would like, this video is getting longer. Okay, in the next lecture what we do is we do not want this not allowed state. I want to remove this now. I have aligned S with the Q and R with the Q complement. I have added the clock here, okay, and I have removed the 1 1 as a memory state and put up the 0 0 as memory state, which is more suitable for us, because we don't want to put up the voltage when it is a memory state. So we have done it, but now I want to remove this not allowed state. And later you will see that being a computer science student, we even don't know. I usually tell people that if someone is mad, okay, being a computer science students, we take his madness to our advantage. We even use that. We don't leave that. So even this behavior is there, we will use even this behavior. Okay? Do you understand what I'm saying? So I hope you got this scenario, but you will not get it if you've not seen the previous 2 vids. You have to go back into the playlist and see the previous 2 vids. That means latch, NOR implementation of latch and NAND implementation of latch. Now I had taken up the LAN implementation, and you can go anytime back and watch those videos and come back here again. And this will, right now it doesn't seem, if you have come without those videos, it doesn't make any sense for you. But if you come with the proper preparation of NAND and NOR implementation of a latch, this is not something scary. This is gonna be fun, and this is gonna be something which you can do very easily. Okay then, see you next time. Until then, ma salama.